Okay. We are having the next speaker. Professor Iro Gelambi, are you here? Hello. Iro, are you here? Jessica and Jack, could you support me by checking whether Professor Iro Gelambi is here or not? While we're doing that, so if anybody have any questions to ask the previous speaker, you can do that. Okay, so I don't see his name in the participation list, unfortunately. Let me double check again. Nope, I don't find Iro's name in the participants list. In that case, I'm going to move forward then. Okay. George, I can see you there. Thank you very much for being here and very much ahead of your time. So we're going to ask you to present earlier then. So
okay, well, thank you for the chance. I will share my screen. Hopefully it's visible.
Yeah, please go ahead. Well, I can introduce you.
Good afternoon, everybody. So I will bring a topic I want to present that is very important for the globe today, and that's fact and myths of European energy transition. Because you read in the newspaper, very often you read some information that is not really fact-based. I don't want to, just in 20 minutes, there's almost nothing as presentation time, but I will try to show you a few typical myths or facts that are linked to the energy transition we have.
That's great. So before you give the presentation, for the audience here, I would like to introduce Georg, and he's a member of the European Academy of Sciences and Arts, member of AAIA-AI, the German National Academy of Science and Engineering, IEEE Fellow, members of Austria Academy of Science, President of the Division of Mathematics and the Natural Sciences of the Austria Academy of Science from 2013 to 2022. Professor, Institute Electrical Measurement and Sensor System at Graz University of Technology. So it's our pleasure to invite Georg to give the presentation on facts and myths of the European energy transition. So Georg, the floor is yours.
Okay, thank you very much. I just want to make a slight correction. I was for 9 years, I was president. My term ended just 2 months ago, so I have a little bit more free time now. Well, anyhow, okay, let's start. So now hopefully the computer lets me start. So. Okay, now it works, I suppose. Yes, okay. So the global CO2 budget for 2050 is shocking.
Georg, can I interrupt you? I can't see your slides, so I don't know whether anybody else can see it. Yeah, okay.
Now I think then we'll try it again. I share the screen. 1 second. So I should.
Yeah, perfect. We can see it. Yeah, we can see it. Perfect.
I cannot go back and forth. Oh yeah, now it's okay. You see the next slide?
Yeah, we can.
Okay, now then it's fine. Okay, so the global CO2 budget till 2025, 2050 is very strict. So global warming is in progress without noticeable effects. And currently about 36 gigatons of CO2 are released annually. And here you have from the IPCC, from the International Planet and Climate Change, a slide, all global models for limiting global warming to a maximum of 1.5 or 2 degrees C called for short-term and significant greenhouse gas reductions in all sectors. Elsewise, we won't make it. And to achieve the 1.5 degree target, it's almost impossible to meet, but we will try hard. With 50% probability, about 500 gigatons CO2 will remain from 2020 onwards. And just to get a flavor, in the last 10 years, from 2010 to end of 2019, around 41 gigatons CO2 per year were emitted. The 20 years before, it was 29.5 gigatons. And in the last 135 years, it was just 10 gigatons. So obviously, the growing of the population and industrialization brought all these CO2 into the atmosphere. And where this comes from? Of course, from the global primary energy supply that the world needs. Here you have a slide where you have from 1960 to 2019, you see the enormous quantity of fossil fuels on the right-hand side for 84.3%. And just 15.7% are low CO2. What means low CO2? You have solar, wind, hydropower, nuclear, but the only, let's say, unlimited resource are the renewables, wind and sun. And in 2019, it was just 3.3%. And this, as this number is so important, I look a little bit into the detail. Again, fossil fuels, huge block. And in there, in this tiny little part, you have wind and solar together, the 3.3%, but you also recognize nuclear is just 4.3% on a global scale, hydropower 6.4%. So even if we double both, we will not make it. So we have to rely on wind and solar. The bad news is that you only get from wind and solar currently electricity. And the electricity is important, but you cannot store it. And I will come to that a little bit later. So when you look to the electricity generation per fuel in 2019, then we have global primary energy was this 162,000 terawatt hours, and global electricity just 16.7%. That's very low. Of course, it's a very valuable, it's a form of energy, but it's not very high. So what does this mean? The world urgently needs more electrical energy, but the world needs predominantly other green and storable energy sources. And electricity is not storable. And the electricity generation, as we've seen here, is just 37% green. So 1/3 is green, 2/3 is fossil. And from the fossil, coal is dominant, 85%. When you look to the industrialized nations like OECD, you have the countries here on the right-hand side, and Europe well, specifically, we have 2/3 green and 1/3 is coal. Thanks to France and to a few countries have many nuclear power plants operating. But again, the fossil part, almost 50% coal. In Germany, it's even worse due to brown coal. It's 64%, so not a good news. And in Austria, we run predominantly, we're running on water power plants and bioenergy. So there it's nice. But anyhow, this is the generation. As the Austrian grid, the European grid is a huge, let's say, copper plate. You will always get the current out with this European mix, 60% green and 40% coal. And this has a big impact on the CO2 emissions. So the largest fossil energy consumers are globally industry and services, followed by buildings, and in wealthy industrialized nations, additionally petroleum-based transport. Energy transition means defossilization. I do not want decarbonization, the name or the term decarbonization, because carbon is a very important element. We live on that. And this element has the, let's say, the huge benefit that it can increase the volumetric energy density of hydrogen significantly. And therefore, I would love to say defossilization, because then it is a biological carbon and not fossil-based. So this defossilization of global primary energy, not just the primary energy needed to generate the 70% of the electricity. The most important target must be electricity from non-fossil sources, and green electricity must grow faster than electricity growth. That's obvious. If we want 100% green electricity and we always invent new consumers, and we cannot catch up with that and even overtake them so that we produce more, then we will never get a green current, and so we can forget the energy transition. So in addition to electricity, it's essential to generate green storable energy in large quantities, like nature has. So 3 measures are necessary to achieve the energy transition. First, save energy, expand green power, as I already said, that's number 1, and generate green storable energy carriers. We currently live in a world where the energy is consumer-based. So whenever you want some energy, you call your power company, or you use some coal or oil or whatever, burn it, and you have energy. In the future, when we have wind and sun, we are no more demand-driven, but we are supply-driven. When sun is there or when wind is there, then we have energy. If it's not there, it's over. So if you analyze that, in 2019, Austria imported 17,100 terawatt hours. Of course, we will have some energy savings in the future, perhaps 50%. But if you just take this number, if you want to compensate for that, or if you want to obtain this energy by wind turbines, we have to come from 82,000 wind turbines. We have to multiply by 36, so we're 36 times more wind turbines to collect to generate these 17,100 terawatt hours. As well, wind turbines, the annual capacity utilization is plus 26%. And if you do it with photovoltaics, it's even worse. With photovoltaics, we have to increase this number by 111 times. So but you gain from this data some important information. Europe is not and will not be energy autonomous in the future. We haven't been. 2019 it was 58%. And in the future, it will also be not autonomous. So we must import fuel. And the question is, which type of fuel? But we have a first caveat: the construction of green infrastructure releases huge amounts of greenhouse gases. So we must really take care and be very sensitive that we do not produce too much CO2 just by producing a green infrastructure. And the second one is, caveat, is compared to fossil energy. The energy density of green energy is tiny. I have an example for you. I take a big wind farm, 1 gigawatt wind farm, 44% usability, nominal power utilization. So this will deliver 3.9 terawatt hours per year. Then we make with the power plant power to X, so power to liquid methane or diesel fuel. The efficiencies very much depend on the process we're using, so we end up with 1.8 to 2.8 terawatt hours per year. And then we need a ship. That's the wind park, like the Baltic Sea, the wind park Arkona, and I multiply it so virtually by 2.6 to come up with round numbers, and we have 100 square kilometers to get 1 gigawatt out of this wind park. And we need a ship to transport it. The ship, liquid natural gas tanker ship, ships the nitrogen cooled down at minus 162 degrees C, and has tanks that take 250,000 cubic meters. And diesel fuel tankers or petrol fuel tankers, they have almost the same size, but the tanks are bigger because they need to be thermally isolated, so they take 350,000 cubic meters. I have a question for you. How long do you estimate it will take to fill the tank ship? As we don't have so much time, I cannot get answers from you. I give you the answer. Operating a wind farm for filling LNG tank ship takes 7 to 10 months, and a diesel tank ship 1 to 1.5 years. Just one ship. And this huge wind park of 100 square kilometers. So this means wind and solar energy have an energy density orders of magnitude lower than hydrocarbons, and the transport losses of hydrocarbons are, thanks to this very high energy density, most negligible relative to the energy content. And the best transport and storage option lies in chemical bonds, either nitrogen, hydrogen, then we have ammonia, or hydrocarbons, CH bonds, for transportation, storage, and use. The consumers in Europe grow. Households, information, communication technology, electric motors, railroads, light, all those need current, and they have no other option. And we cannot transport current between continents, like hydrogen. We cannot transport it. Secondly, commercial industrial sectors need to be fossilized. Of course, an increase of the efficiency is urgently needed, and the primary energy demand decreases at the expense of more electricity demand, because usually efficiency increase means some electric stuff. You can have process heat with heat pump, heat and cooling of buildings and manufacturing, again, heat pumps for more electricity. The conversion of crude steel from coal to green hydrogen requires in Austria at least 30 terawatt hours. That's a little bit less than 50% of the whole Austrian current consumption, so that's almost double. It's amazing. In Germany, it's just 1/3, but it's a huge, huge number, hard to collect. The conversion of German's chemistry requires almost the same energy whole Germany needs today for current. Again, for green hydrogen. Conversion of German refineries, again, big numbers. We have to produce with wind power or solar power and make out of that green hydrogen for the industry. And all these green hydrogen has to be produced on the continent because we cannot ship hydrogen. So the basic material industry, it's responsible for 6% of the fossil CO2 emissions in the European Union. Large amounts of electricity are needed to produce green hydrogen, predominantly for high temperature use. So policymakers should answer and act accordingly on the following question. In which consumption sector does state funding produce the greatest sustainable fossil CO2 savings? Because that's a myth that we hear from politicians that, let's say, electromobility is a good idea currently, perhaps in 20 or 30 years, but not now. So the impact on the energy on transportation in Europe is, remember, only 70% electricity. The industrialized nations need about 35% of the primary energy, that's predominantly crude oil, for transportation, for the transportation sector, and about 2/3 is used for passenger car transport. In metropolitan areas, the drivetrain efficiency, that's the energy at the wheels, referred to the energy in the storage, tank or battery or whatever, is for internal combustion engine cars just 15 to 20%. But for battery electric vehicles, 80%. And this is the deceptive temptation. If you drive, and again, a myth, a deceptive temptation for the politicians. They say if you drive a battery electric vehicle, you can save 80 to 85% fossil primary energy. So we must do that. We must support it. We must finance it. But that's a fallacy. Not the battery brings the high efficiency, but the electric powertrain, because electricity in Europe is only 60% green and 40% fossil. You've seen 64% is coal. And the volatile energy is always in the grid. So if you add some consumers, you must have an additional power plant to supply. And this is fixed in the so-called merit order. So the missing electricity, this residual current, and it's fixed in the merit order, must be provided by fossil power plants, which are also essential for grid stability. Let's have a look to the merit order. So here you have the marginal costs on the left-hand side, and on the graph below, the specific emissions in gram per kilowatt hour. So nuclear is very cheap. The same with lignite. Unfortunately, right, the other way around, the CO2 emissions of brown coal are very high, followed by hard coal and so on. So when we introduce an operating point without battery electric vehicles, and now we put some battery electric vehicles to the grid, then of course it has to be provided only by those power plants that are given here. this means with battery electric vehicles, you will supply them with this residual current. And this means the primary goal of the energy transition is 100% grid defossilization. Boosting any additional electric grid load through public funding needs additional fossil power plants and thus delays the energy transition. Let's have a look to, as an example, electromobility in Germany. If we assume 2019, all passenger cars are battery electric vehicles. The installed power plant in capacity in Germany is 214 gigawatt, and the average load of the German grid is around 75 gigawatt. In this graph, you see here the simultaneously charging electric vehicles. So 0 to 10%. Why 10%? Because the European Union says for each 10 cars, there should be one public charging station. And here you see the additional required grid load. So if we assume just, let's say, 4%, yeah, and here the base load is this 75 gigawatt, as said, that's average load in Germany. If we double it, then if I just load it with, let's say, 25 kilowatt charging for 60 minutes, 25 kilowatt, then we have 6% of the cars in parallel on the grid charging, then we already double the load. And with 50 kilowatt, it's even worse. So this means the grid will not take these very high loads. If not for a long time, big amount of money is invested into the grid to obtain it. And in a dense populated area like Europe, it's very unlikely. If you just compare it to a diesel car, if you recharge a diesel car, let's say 600 kilowatt hours in 3 minutes, the next time when you do that, your hose is then a cable, but this cable represents a 12 megawatt plug. So the resume for Germany is electrical charging would mean 179 terawatt hours per year more. In wind turbines expressed, it's 137% more. Wind power plants or photovoltaics, you have to almost 4 times increase it. Free access to the 4.7 million charging points will make the grid collapse, as already explained. Mobility has other options than electricity, and that's the clue. ICT households, electric motors, as already said, they need their fixed electricity. And of course, green hydrogen for the refineries to defossilize the industry types I mentioned already. So the electric powertrain is ingeniously simple, low cost and has high efficiency. Just do not store the onboard energy in batteries, convert it on board from green fuels. This should be made. So politics should question whether it's not irresponsible to use public money to promote a form of mobility that will not work when fully deployed. So how to make an optimal use of the electricity in Europe is the following. Wind and solar energy provides electrical energy that must be consumed because electricity has no energy. This is the long list who really need that. In a first lossy energy conversion process, you produce green hydrogen. Currently, we do not have another way. We must produce green hydrogen and from electricity, and this means with electrolysis for the industry. In a second lossy energy conversion, we can produce synthetic fuels, whatever type we want, but more losses. We can produce methane, ammonia, methanol, petroleum, diesel, everything out of green hydrogen. So minimizing the number of energy conversions, minimizing the primary energy demand, minimizes raw material requirements and thus greenhouse gases, and build the infrastructures for green energy vectors, and minimizes, of course, the capital expenditures and the operating costs. So the summary of my presentation is greenhouse gas reduction is a global issue and not a local. The rich and technology-leading industrialized nation and the poor emerging economies jointly determine achievements of the Paris goals. 5 measures needed immediately to implement Europe's successful energy transition. First one is immediately effective global greenhouse gas reduction strategies. This means proposals for saving energy in order to get by with less primary energy, especially in transportation, without sacrificing well-being. Secondly, defossilize the European electricity network with the highest priority and only grant state subsidies to electric consumers who can clearly demonstrate that they meet the efficiency criterion and thus contribute to the defossilization. This applies, for example, to heat pumps, but not for electromobility. And finally, produce green methane and synthetic liquid fuels at high yield locations worldwide in cooperation with local decision makers and import some of them to Europe. Some keep at those growing nations because they need also green energy, and some import to Europe. Fourth, creation of political framework conditions for planning and legal certainty for investments with lifetimes of good 50 years. The energy transition requires billions of euros in investment, which must be raised primarily through venture capital in order to build green power plants in countries with favorable site conditions. And finally, policymakers act in a technology-open manner. Currently, they do not. They say which technology should be used. They leave it to the science, companies and consumers to come up with solutions that work and do not have a say in the selection of energy transition technologies. And the facts presented in a program of measures must be discussed in a large social dialogue in order to establish a scientifically sound and fact-based energy transition without any myths. Thank you for your attention. And sorry for 2 more minutes. Thank you.
Thank you very much for a wonderful presentation on energy transition, and especially when we think about the current energy crisis in Europe. So it's really, really great to hear you talking. George, I'm going to use my chair privilege to ask you a question. Like what you said, there's a lot of myths and wrong statements made by politicians in Europe and in UK, in quite a lot of places. So my question to you is really, as a scientist and engineers, how we can educate the public as well as the politicians and policymakers to really make them, to ensure they make the right decision. So I think of not only we should advance science, we also need to educate these people. So what is your view on that?
I would say all fact-based engineers and scientists should educate politicians, should educate the media that they stick on facts. And whenever you read those myths or from the politicians that they say we do this and that, they have no idea about that. They are responsible to, let's say, make contracts. As I said in the last few slides, they must make contracts with countries where you can collect at least double amount for the same number of windmills and photovoltaics, because elsewise we will just, let's say, set so much CO2 free, fossil CO2 free, to build the infrastructure that we can forget the 1.5 or 2 degrees C goal. So it's our duty to pack it into messages they are able to understand. As simple
totally
as
agree
possible.
with you. Totally agree with you. I think it's nowadays for scientists, not only you should do research, but you also need to think about taking every opportunity to educate the public, the medium, and the politicians. So thank you very much again for your wonderful presentation, George. Thank you.
Okay, thank you. You can take the presentation right back, I suppose. I think. Okay, now I think I stopped it.
Yeah.
Now you can.
Okay.
Yeah, okay, that's fine.
Yeah, thank you very much. Yeah, okay.